Cold fusion. Atomic power from water. No radioactive materials, no radioactive waste, and no CO2. Cold fusion is power for the people, where no community can be denied access to fuel. With 10 million times the energy density of fossil fuels, it could provide energy for the whole planet for billions of years. Researchers are trying to make a technology while still understanding the science. And almost 3 decades of experimental research have produced a variety of startling effects. In 1989, Drs. Martin Fleischmann and Stanley Pons announced their discovery of an anomalous fusion-sized excess heat energy generated by palladium and deuterium cells. From these types of cells, tritium was found, but always in amounts millions of times less than hot fusion and without the commensurate neutrons. The production of helium was correlated with the excess heat using palladium and deuterium, while nickel and light hydrogen produced weak gamma photons. Today, low-energy nuclear reactions, or Lehner's experiments, have produced soft X-rays, coherent laser-like photons, and exhibited superconductivity. And 2 types of transmutations of elements have been achieved in multiple Lehner environments, including biological systems. How can such a wide variety of effects result when hydrogen interacts with solid materials? Theorists struggle to find an answer. Nobel laureate Julian Schwinger remarked, "The circumstances of cold fusion are not those of hot fusion, for conventional nuclear theory does not explain these laboratory observations." No recipe to both initiate and scale the effect exists. Laboratory successes are won by trial and error. But a new idea is transforming understanding. Dr. Edmund Storms is a nuclear chemist who has conducted many surveys of the field and written 2 books on the science and theories of Lehner. His experiments have shown that temperature is the single most important factor to regulating Lehner excess heat, and that high loading is not necessary to maintain a reaction in palladium-deuterium systems. He has put together the first physical science-based description of Lehner, utilizing the tiny nanospaces in materials as the nuclear active environment, where hydrogen assembles to form a unique structure able to initiate nuclear fusion through resonance by a new, as yet unknown atomic mechanism.
We've spent 24 years proving to ourselves first and then to the world that this is real. It's a physically real phenomenon. Now the problem is we have to convince ourselves and the world how and why it works.
Nothing about this violates conventional theory. It adds to it. This is a new, undiscovered phenomenon.
When it occurs in hot fusion very rapidly, the energy comes out in one big burst. That is, let's say they're deuterium, they come together momentarily and then they blow apart immediately in different combinations of neutrons and protons, carrying the energy with them. And so they go boom, boom, instantaneously, and the energy comes off as energetic particles. In cold fusion, they come together very, very slowly, and the energy goes off as photons, gradually, as they get closer and closer together. That's the distinguishing characteristic, and that's what makes cold fusion truly unique as a nuclear reaction. That slow interaction is not the kind of interaction people have experienced in the past, nor have much understanding of theoretically.
The more ways in which nature has to do something, the easier it is to occur, and the more often it occurs in nature. This occurs in nature very, very seldom. And it's very, very difficult to duplicate. So therefore, it must be something fairly rare and therefore very unique. And therefore, it says that nature really only has one way of doing this, and unless you have precisely that arrangement, that nuclear-active environment, it's not going to happen.
It requires a significant change in the material to occur, and that getting that change in the material has been the real big problem to make the effect reproducible.
Right now, we're creating that environment by accident. We just throw a bunch of stuff together, and a few places at random happen to have the right combination of materials and relationships to one another to work. So most of the samples, maybe less than 1%, are active.
The effect does not occur throughout the sample. It occurs only in special, very rare, randomly created regions in the sample. I call this a nuclear active environment. Presumably, the more of these sites are present, the more energy you'd be able to make. These samples would have had only a few of these active sites, and these samples would have had a large number of active sites. This becomes a probability distribution, showing that the probability of having a large number of sites were very low, and the probability of having a few sites were very high. And of course, this extrapolates to zero, having a very high probability. And that's why it's been very difficult to reproduce.
I assume that something changes within the material, and I call that change the creation of the nuclear active environment.
It has to be something that is universally present in all of the experiments that work, no matter what method is used, no matter what material is used, no matter whether it's light hydrogen or heavy hydrogen.
Now, what are the characteristics of the nuclear active environment? Well, we know a few of them. We know that you have to have deuterium or hydrogen in that environment. We know that the higher the concentration in that environment, the faster the reaction goes. We know that something in that environment is capable of hiding the Coulomb barrier of hydrogen or deuterium. We know that something in that environment also is able to communicate the energy to the lattice rather than have it go off as energetic particles. So we know just from the way in which it behaves certain overall characteristics, but we don't know the details yet. But when I say, okay, let's talk about the nuclear active environment, I'm saying let's talk about where those details are located in the material. We want to look where we expect that material to be located. I expect it to be located on the surface.
The challenge is to figure out what about the surface is universally related to a sample that makes excess energy.
When people have used solid pieces of it, all except for the last few microns of the surface are totally dead. So all you need is a few microns of palladium on something else. And I put a few microns of palladium on platinum. It works just as well as a solid piece.
But after examining hundreds of these photomicrographs by other people and by myself, the only thing I could see was common to all experimental methods and experimental conditions were cracks.
In hot fusion, you overcome the Coulomb barrier by brute force using high energy. In cold fusion, you overcome it by lowering the Coulomb barrier using electric charge. So you have to have a condition in which the electric charge is suitably large, and cracks have the potential to produce that kind of condition.
Well, that seems crazy because for a long time in the field, people felt that cracks were bad. They allowed the deuterium to leak out of the palladium.
And we see that happen because if you put some of this material that has the cracks in it in a liquid, and you can see the bubbles of hydrogen coming out of those cracks.
And so they were ignored, or people were trying to avoid them. And what I propose is that the crack has to have a particular size, and when it has that size, it allows the nuclei of either a deuteron or a proton to come into that and set up a series of, let's say, proton, electron, with the electron being between each of the nuclei, thus hiding or reducing the Coulomb barrier. Well, the size of the crack is something that will have to be determined. They have to be small enough that they would not allow the hydrogen molecule entry, because we know the hydrogen molecule does not produce a nuclear reaction. They have to be big enough that a single nucleus of hydrogen can go in there and be retained and not interact with it in such a way as it would in a chemical state. So I'm guessing something in the less than 10 nanometers.
Cracks always start small. Cracks always start at the size that would be nuclear active, but only for a short time.
The holes themselves are not the active, they only give you the indication that that stress reorganized the surface. What I'm saying is that stress also produced the nanocracks in the walls of these holes. And that's where you have to look to find the genie of cold fusion.
The nuclear active environment is proposed to be a nano-sized gap that hosts a unique form of hydrogen. While large spaces and cracks allow hydrogen to escape the material, tiny nano-sized gaps are small enough to retain a single nuclei of hydrogen in a covalent chain called a hydroton. Subjected to the high concentration of negative charge in the walls, the electrons shared by the hydrogen nuclei are forced into a more compact state with an average smaller distance between nuclei. But what happens to create a nuclear reaction?
Whatever it is, has the ability to initiate a number of different kinds of nuclear reactions. One makes helium and heat, another one makes tritium, another one does transmutation. So there's a variety of things that can happen in that environment.
And all behavior using all isotopes of hydrogen can be explained by a single basic mechanism operating in a single nuclear active environment.
I mean, that would be a lot to expect for something so unusual as this to have a variety of ways in which it can happen.
By sheer probability chance, there's a crack form. It has to have the right size. And then because of diffusion, they start building up a concentration in the crack.
Hydrogen, when it gets into this gap, forms a covalent chain, which I call a hydroton, with the release of Gibbs energy, and that stabilizes the gap.
Hydrogen can form a chemical compound that has lower energy than any hydrogen anywhere else in the material. So the hydrogen migrates there, forms this compound, and because that compound is more stable than any other, it cannot decompose without that energy being reapplied to the hydrogen in order to get it out of there.
Because that's occurring in a chemical lattice, it follows all the rules of a chemical reaction.
That narrow crack would have a very high concentration of electron or negative charge on both walls, which would force the hydrogen into a structure that I believe would help hide the Coulomb barrier and would help the resonant process take place.
All right, once that builds up to a sufficient number, something triggers it. That can just be the normal temperature vibrations because everything's at an atomic level is vibrating.
But because it has a linear structure, it can start to vibrate such that these two come together, these two further apart, these two come together, and so forth.
All right, so these things start to vibrate in line. And when they do, because you have charges moving, you have the prospect of photons being generated.
When these two come together, they find themselves too close. They have too much energy, too much mass for the distance because they're on the way to having formed a fusion product.
Now the system knows that if it collapses, gets closer and closer together, it will gain energy because the end product is a nuclear product that has less mass than the sum total. So it knows that that's the direction to go. So it just keeps giving off photons.
Finally, enough's given off that each time they get a little closer, they give off a little bigger photon.
Each time it gives off a photon, it collapses a little more, another photon, a little more, a little more. Meanwhile, vibrating, photons are streaming out. Finally, the last photon goes off and it becomes a deuteron, because the electron that was between them gets sucked into the final product.
But there's hardly any mass energy left over at that point, so this becomes stable, or if not, gives off a very weak gamma.
And then that's deuteron now there. Now that deuteron, if there happens to be another proton or another deuteron in there, it can start the process all over again. If another deuteron happens to be there, then it can make helium. Or if a proton happens to be there, it'll make tritium. The deuterium then has a choice. It can diffuse out, in which case it'll be replaced by a proton, more likely, because that's what's in the general environment. Or it can stay there and another proton comes in and it starts to fuse and it makes tritium instead.
Well, it is symmetrical as these things bounce. It isn't just when they bounce this direction they give off the photons. When they bounce this direction they give off photons also. So these things are bouncing in a symmetrical way. Each time they go this direction they lose mass, and then they come back together and lose mass. At some point they've lost enough that these two guys don't bounce and they stick together, and then these two guys over here stick together.
And so the question is, where during that process do they recognize that they have too much mass and have to get rid of it? When you do it by hot fusion, that's done very, very quickly, and it overwhelms this process. I'm proposing that this is the unique feature of cold fusion. This is where cold fusion differs from hot fusion.
Cold fusion is slow, it's methodical. Because it occurs over a period of time, the energy has time to get out in small quanta.
Now, that electron has to have very special properties, and that's the only thing that is novel. This is total, consistent, normal physics, except for that electron and its characteristics. So something new has happened, has been discovered, is required to make cold fusion work.
Crack is not destroyed. The crack is a manufacturing tool. It's just simply there, and atoms go in, fuse, and the products diffuse out, maybe, or they stay there. More stuff fuses. It just simply is an assembly line of the fusion process.
That crack becomes attractive, and it's also attractive because it's very difficult to produce, and it's outside of the thermodynamic characteristics of the material. In other words, cracks can occur in any material regardless of its thermodynamic properties.
Nanospaces allow a different form of atomic interaction to occur, where hydrogen nuclei and electrons can form a chain called a hydroton. Pulsing in resonance, periodically smaller distances coax nuclei into a slow fusion process, where smaller bits of mass convert to energy through coherent photon emission. An electron is absorbed to make the final product. All the isotopes of hydrogen are proposed to behave the same way. Any other element in the gap resonates to transmutation.
That's why cold fusion was essentially rejected by people who were educated and had experience with hot fusion, which plays by entirely different rules. Cold fusion plays by rules that we don't presently understand. And those rules involve a slow interaction and a slow release of energy.
I also say that cold fusion has to follow all the laws of nature as we presently know and love them. They cannot violate any law of nature, chemical or physical. The only problem is that there's something missing in those laws. So it isn't that they're conflicting with anything, it's just that we don't have all the pieces yet.
That's the big, what would I call it, the big discovery, that a chemical compound of hydrogen created under very special circumstances can then fuse.
Nano-gaps and hydrotons are able to explain the broad variety of evidence in letter experiments by reasoning that follows the data and begins with tritium production.
Tritium provides a the key to understanding this process. And tritium also provides the way in which the process can be verified. Tritium is made in these cold fusion cells. But tritium cannot be made by the hot fusion reactor because we're not seeing any neutrons. So it has to be made by some other process. Well, there are a limited number of ways in which you can make tritium. When you examine all of those, you discover that the only thing that really makes any sense is this reaction here. The deuteron fuses with a proton, captures the electron, makes tritium, which then decays by its normal decay with a half-life of 12.3 years to helium-3 and an electron. All of the isotopes of hydrogen have to behave the same way.
If that's the only way you can get tritium, then it's also the only way you can get helium. The electron also has to be sucked in.
That means the deuteron fuses with the electron, that makes hydrogen 4, which decays very, very rapidly, so we don't see that accumulate, to make helium 4 and, of course, the electron as part of the decay.
Hydrogen 4 does not decay normally into helium 4, but it has to for the cold fusion thing to work, because if this is an exception, if the electron doesn't get sucked in, then my whole model starts to fall apart, because where in the heck does that electron go? It has to be there in order to hide the Coulomb barrier. It's there in the other two reactions, so why isn't it there in the helium? So right there, normal nuclear expectations break down.
The Hydroton is a whole new world that now cold fusion and Hans and Fleischmann have revealed exists. It was totally invisible until they came along and said, hey, wait a minute, here's something that can only work if the rules change. And so you better start looking at new rules. And the Hydroton is, in fact, the structure that makes those rules operate.
I've taken these various ideas. Many of them are not original to me. What is original is to putting them together so that they have a logical relationship. And then on the basis of that relationship, they can predict precisely what's going to happen. There's no wiggle room in this theory. I mean, I'm not like most theoreticians. Okay, if that doesn't work, I can adjust some of the parameters here and make it work. No, it is either right or wrong. It's as easy, simple as that. I either go down in flames or I'm right. And the result is that suddenly I can make sense of cold fusion, and suddenly now I know how to make it reproducible. And once it works, I know how to engineer it. So the only problem is I haven't yet proven that.
Beginning with experimental facts and following a logical process of reasoning has produced both questions that challenge the standard model of nuclear physics and provided testable predictions that will confirm or deny the nano-gap hydroton hypothesis.
I predict that the hydroton is metallic hydrogen. This is that mythical material that people have been looking for by squeezing hydrogen at very high pressure. That is precisely what is formed in this gap. The gap makes that possible. The reason why metallic hydrogen has been very difficult to detect is because once it forms, it fuses. That allows us to harvest the mathematical understanding of metallic hydrogen, which is already in the literature, to explain this material and also relate what we're seeing to another kind of measurement.
Cold fusion represents a whole new way of looking at nuclear interaction, the rules of which will have other implications and it will have other applications, and will allow us to do things that we can't even suspect can be done now, including the deactivation of radioactive material that we have generated by virtue of the other energy sources.
Only experimental results will validate the hypotheses of the nano-gap hydroton model. New data supports the hydroton prediction that the amount of tritium is related to the deuterium to protium ratio in the fuel. To confirm the nuclear active environment as a nano-gap, creating the right-sized nanospace that hosts a reaction with 100% reliability is crucial. Determining if light hydrogen systems are producing tritium is an important next step. Laboratory evidence that identifies emitted photons as coming from a particular reaction would be defining for the Hydroton model. Cold fusion technology will be a radically different type of power, creating a paradigm shift in global operations. A mere 1 cubic kilometer of ocean water contains fusion energy equal to all the world's oil reserves. And a nano-sized source of power holds the promise of a defining next step in our human evolution.
What we have to do is find a way of encouraging a material to create that structure in the presence of hydrogen. It doesn't do any good to try to create it in the absence of hydrogen, because in the absence of hydrogen, the crack will just simply continue to grow. And if you put hydrogen in later, it's too big. It's no longer nuclear active. So you have to have the hydrogen present simultaneously with the formation of the crack structure. And that's the secret of the process. You have to have these two things happen simultaneously.
Well, it's like opening a window, and you open it a little bit and you see a little bit of what's outside, and it looks really interesting. You open a little bit more, and then all of a sudden you realize, wow, there's a whole new world out there. And so this theory has opened that world into a way of looking at cold fusion that hasn't really been explored in completion.
My guess is that once we understand how it works, we will find some other metal or some alloy, or maybe an alloy of palladium and nickel, and some combination of palladium, of deuterium and palladium and hydrogen that will be even better than what we presently have. See, we're nowhere near the ideal at this point.
Is that my theory tries to address the big reactions, the ones that are producing heat. Those are the ones that are going like gangbusters. Now, at lower levels, there's all kinds of little things that are going on, really weird things. They're the things that 100 graduate students will work on for 20 years to really master and understand. And they'll give the details about this mechanism that's going on, and they'll generate the Nobel Prizes, and everybody will be really happy about understanding this physics better. My theory tries to address what's happening at the highest rate level. And at that level, it's fairly straightforward.